Hello everyone, I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT BHU. I am here to take a problem session for the subject of design of photovoltaic system, which teach by the Professor Alumanan sir, Division of Electrical Electronics and Computer Science, IC Bengaluru. I will take your assignment problem session, but I can't be taken your live assignment problem which is given by the NPTEL to you, but we can help to solve the problem, and I can solve the I will solve here related to the your assignment problem, like a previous assignment from previous assignments and other questions related to your assignment, but we can't be solve your live assignment or current assignment. Okay. If you have any doubts related to this, please leave a message on chat box. The design of photovoltaic system is mainly as a solar PV system, which is a renewable source of energy. You all know very well, and it's also a non-conventional energy sources. In all of non-conventional energy sources, solar is very important and is easily available at anywhere at that time, and it is easy to take energy from solar by the solar energy, solar PV.
Hello.
Yeah.
Yeah, good evening, sir. Sir, I have a
Good
one
evening.
doubt.
Yes. Tell me.
Sir, during the lecture, sir told the load line concept for the two similar solar module, right, sir?
Okay.
But sir, my question is that what will be happens if we connect the two dissimilar solar module, like one is a 50 watt and other one is a 80 watt, then what will be the effect on the load line, and why we always connect the two similar modules in the series or in the parallel, not two different ratings? That is the problem, sir.
Okay.
Sir, problem is clear, na?
Yeah. But
Okay, thank you, sir.
but
Thank you,
wait,
sir.
wait. I will hear for the 12 weeks, and
Okay, sir. Okay,
and
sir.
your problem related to the another chapter. That's why wait. Sir, also discuss to you. If you not discuss, I will also discuss
Okay, sir. Thank you,
related to
sir.
the. Okay. This is only for the first chapter assignment. Okay. I will discuss later related to the load lines of a PV cells, how it will work and how it react and for these similar PV panel. I think you will know about the PV cells, really characteristic like PV PN junction diodes. It characteristic like a PN junction because of the PV panel made by the PN junction diode. PN junction panel, and when sunlight is reached to panel, it will react as a depletion layer, reduce the depletion layer, and make a depletion layer, and voltage will be developed there. That is used as a source. This is the anode of the diode, and this one the cathode. VAK, you know very well. The circuit for a diode circuit. This one the current for diode. All you know the direct diode characteristic like that. This one the IV characteristic, voltage, current. This in the reverse direction. But solar PV is work as a equivalent circuit as a constant current and a diode parallel to the diode, because it will this diode is act as a source sink at this time. If the current enter through the anode, then that diode is work as a sink. But PV panel is the PV solar photovoltaic system is work as a source. That's why it will represent like a current source, a constant current source, and a diode. Same diode connected here. This one is the system. In the photovoltaic current, I represented the IP. This one a diode current ID. This one a constant current photovoltaic current like IP. Suppose if you have a constant current IP, I, this one is a B characteristic. If you subtract diode current from this one, this one for a diode, then you can find a solar PV IV characteristic. At a time of 0, the whole IP is represent here, and if you increase the voltage, IP is constant, but this one diode current will be take. That's why this characteristic looks like a reverse characteristic of the diode. Where current is 0, it means open circuit voltage. Where current is maximum, voltage 0, this one is short circuit current. This one is the IV characteristic of the solar PV. It means one constant current is a photovoltaic current passing through a diode. Multiple diode is subject to the diode current like that, and then you find the actual characteristic of the solar PV. Is have some disruption between there. If you passing a load line like that, is a constant voltage VOC here, and then constant short circuit current, then you find the state find is ISM VOC. Okay. So sorry. Now it is clear. This one is represent a series and parallel connected of the resistance. If a resistance connected in a parallel, it means the current will be reduced because of the current sum of current passing through the shunt resistance. It means if current will be reduced here, some it means sum of current passing through a shunt resistor, and here some voltage also reduced to the load line. It means some of voltage drop occurs in the series connection. That's why a final equivalent circuit of the PV panel is drawn like a constant IP current in a diode current after the shunt connected resistance because of the distortion in the current will be reduced. That's why, and voltage also reduce at that point. Then it will series connected resistance. It means this one RS, this one RSH, This one is PV voltage V. This one PV current I. You can say this one ID current. This one a current IP. ISS. This voltage you can written as V plus I into RS. This voltage plus of this voltage drop. And if you want to written as a whole photovoltaic current is equal to ID, same this current, ID plus ISS, shunt current, and delta current passing through the terminal. Okay, everyone. Shunt current you can written as just shunt current is on the voltage divided by a resistance V plus I into RS divided by a shunt resistance RSS. And diode current, I think you all know about the diode current is saturation current into e to power minus, sorry, diode current is equal to saturation current into e to power V divided by NVT minus 1. This one is the diode current. So like a VD, voltage across the diode, and here voltage across the diode is the V plus I into RS. Then you can replace this one VD I naught into e to power V plus I into RS. This one voltage, this voltage same as this voltage, same as this voltage, voltage across diode divided by NVT. This one is the diode current. Then question number first you can written as IP is equal to ID, which means diode current, is I naught e to the power I into RS. RS is the series resistance divided by NVT minus of 1 plus shunt current V plus I into RS divided by RSS plus terminal current. Question number second, you can find the PV current, output of PV current like I, photovoltaic current IP minus of diode current, this one I naught e to the power V plus I into RS divided by NVT minus of 1 minus V plus I into RS divided by RSS. This one is solar PV current equation. Is the screen visible to everyone? Sorry to everyone, I have some technical error here. Sorry. Okay, everyone. I think some problem. Voice is clear. Please remind
Yes, sir.
me. Sorry, some technical issues occurs here. That's why. Okay. Here the current, solar current, noted as I is equal to IP, means photovoltaic current, and I naught into E to power B plus I into RS, and BT is a diode current, and remaining is the shunt current flowing through the shunt resistor. You know about the BT, so the volt related to the volt equivalent temperature, the T is equal to T divided by 11,600 for the silicon, where N is equal to 2. Okay, if you want to find the short circuit and open circuit voltage for the solar system, for any cell, this one is the voltage and I characteristic. This one is the open circuit voltage, short circuit current. Then how you find the open circuit voltage and short circuit current of the whole cell? At IC point, voltage is equal to 0, then current is equal to short circuit and voltage is 0. We put the all of thing, all the voltage and current in the equation third, and you can find equation like I short circuit current IC equal to IP minus of Y naught e to power V is equal to 0 at the short circuit current. At the short circuit of terminal voltage will be 0. Then you can written as I into RS. I is equal to ISC into RS by NVT minus of 1 minus of ISC into RS divided by RSS. In this equation, the series resistance will very less according to respect to the shunt resistance. That's why you can neglect this term. And same thing here. This is the series resistance very low. So this one term is representing like equal to approximately to 0. That means 1 is 0. E to power 0 is equal to 1. 1 minus 1 is 0. The whole part will be 0. Very less value of this one, approximately 0. That's why you can retain as I is directly I is equal to approx current of IP. Series connected resistance of anywhere connected series resistance is very low it compared to the shunt, because of if you can observe is this one from here. So no, current will be very low here. Maximum whole of current is passing through this one. The less amount of current only passing through the resistance of shunt, but voltage drop is huge here. If you can observe this one, voltage drop is more. If this less amount of current flow through the shunt resistance, it means the shunt resistance will be high. But if series resistance is very, if you can take, if you want to take a very high equal to the shunt resistance, it means the whole of the voltage is dropped at a series resistance. but it did not happen in the solar PV. Very less amount of voltage drop at the series point, means this one. That's why say in the series connected resistance will be very low with respect to the shunt resistance, because of the very less amount of current flow through the shunt. That's why you can neglect this one. Then you can find the ISC directly proportional to the photovoltaic current. This one for the short circuit. If you want to take a open circuit characteristic, this is short circuit characteristics, then find the short circuit current. You want to find the open circuit voltage, terminal take a open. The open circuit at open circuit terminal, it means the current will be 0, I will be 0, voltage is open circuit voltage. Then same equation number third, you can replace I current in voltage. I is equal to 0, means this one will be 0. IP is a photovoltaic current, will sum about, it will be constant because of the solar IP is the photovoltaic current. It means from the, it will be from the solar radiation, depending on the solar radiation. Solar radiation is constant, it means that this one is a constant current flowing. But at a terminal of solar PV, the current will be 0 because of the open circuit. It means the whole of the current flowing through the sun and diode. This one is IP minus I naught diode current e to the power I is equal to 0, so V divided by NVT. V is equal to VOC NVT minus of 1. Now this one is I current is 0, V divided by RSS. So it's VOC. Same thing here, if you observe this one, a cell voltage. This one is a cell voltage, not a whole module voltage. We drive a cell voltage current, short circuit current, and cell voltage, open circuit current voltage. It means the voltage, open circuit voltage is very less amount of with respect to the shunt voltage. It means this one is 0 to I think 1 volt only, the cell voltage. The number of cells are connected in series and parallel to make a module. A number of module connected to make a panel. That's why the cell voltage is very less compared to the shunt resistance. Shunt resistance, it means very high, like 100, 200, 500 volt. Sorry, ohms. That's why you can also neglect this one. Then you can find the output voltage, open circuit voltage. It will be IP is equal to I naught e to the power VOC divided by NVT minus of 1. And e to the power VOC divided by NVT is equal to IP divided by I naught plus a 1. It implies you can take a logarithm of this one, you can find VOC divided by NVT is equal to ln IP plus I naught divided by I naught. From this equation you can find the open circuit voltage NVT ln IP plus I naught divided by I naught. So the question of open circuit voltage, and this is the short circuit current. You can observe this one, the short circuit current is directly proportional to the photovoltaic current, and photovoltaic current is directly proportional to the radiation, irradiation, like you can say insulation. Insulation is the parameter to define the power, actual power of the solar radiation. Insulation defined in the kilowatt per meter square in the per hot amount of power delivered in a unit area. But here the open circuit voltage is not directly proportional to the IP. It has the algorithm. It means if change the insulation, the current will be changed suddenly, but voltage will not more changes. Very small changes in voltage, open circuit voltage. But short circuit current will be changed linearly. You can say that this one is the open circuit, short circuit current is changes linearly here with respect to the insulation. But in open circuit voltage change is in logarithmic way. It means if you want to draw say at same graph to increase the insulation of a solar panel, then you find that this current will be changed like that, but voltage will be very less changes like that. So anyway, increasing of insulation. There the question number first is says that the short circuit current and open circuit voltage of a PV cell varies respectively. Then you observe this one, the short circuit current directly proportional to the IP, or approximately is to IP. IP directly proportional to the insulation. But voltage VOC is approximately equal to NVT and log of IP plus I naught divided by of I naught, where I naught is the reverse saturation current of diode. IP directly proportional to the insulation. It means VOC is proportional to the logarithmic of the insulation. It means short circuit current varies linearly to the insulation, but open circuit voltage is varies in logarithmic way. The question was second is given what can be inferred but about the values of series resistance and shunt resistance in a PV cell having a very low fill factor. Fill factor Fill factor is represented as the utilization of any solar PV, a solar cell. It means open circuit voltage and short circuit current. With respect to the short circuit current and open circuit voltage, what is the P maximum power? of any solar PV, a solar cell. This one the IV characteristic. Short circuit current, open circuit voltage. If you see this one, it's on VOC. In this one, yeah, ISC. If you want to find the power, max change the VOC into ISC, maximum deliverable power of any solar PV. But you find this much power only. You can want to find the maximum power of this one, it will be like that. This area can't be exceed this one power of any PV panel because of the shunt connector resistance and series connector resistance. This was the maximum power you can say at that point. This point is the IMP and that point is the VMP. Then what is the power? Power is PMP, the maximum power. There is a saying that what can be inferred about the values of series resistance and the shunt resistance in any PV cell having a very low fill factor. So in fill factor is output. This will VM divided by a VOC into ISC. If the maximum power is same as this one power VOC and ISC, then fill factor will be 1. But because of the series connected resistance and the shunt connected resistance, the sum of the power is be lost in the circuit. That's why fill factor will be less than 1 of a practical PV cell. Then you say what is the very low fill factor? Very low fill factor, it means if you increase the series resistance very high, it means the voltage drop is very high. The VOC come through the hair to the very high, and shunt resistance is very low. The lot of amount of current flow through the shunt resistance, not flow through the terminal resistance. The shunt will also reduced here like this one. If you increase the series resistance and reduce the shunt resistance, then you find this sequence, this flow graph is flowing like this only. That amount of current and voltage will be reduced and power also reduced. This reduction, from here at IC point, at a minimum point you can say like a flat line. This one will be minimum point, minimum of, if you want to VOC, this one will be minimum flat line. Minimum fill factor. If you want to find a power at that point, this will be the power, because this is only because of the series and shunt connected resistance. That's why it's ask about the very low fill factor. It means the series resistance is very high and shunt resistance is very low. If that phenomenon occurs, then the power of any cells, PV cells, is very reduced, very well. But, That's why it should be a RS is very low and shunt resistance is very high to find the fill factor high. And also you can say the utilization factor. The fill factor of an ideal PV cell will be ideal PV cell. I think you all of know about the ideal. If ideal, it means RS is 0, shunt is infinity. It means this graph, so this one is a practical graph, but in ideal cases this one will like that. VOC same as VM and ISC same as IM. Then what is the fill factor? Fill factor will be 1 at that time for the ideal cases. VM, IM and VOC and ISC is only same as VM is same as the VOC and IM is same as the ISC. That's why the fill factor will be 1 at that time for the ideal cases. The ideal cases it means series connected resistance will be 0 and shunt connected resistance will be infinity. That means same of ISC and VOC flow at load. Which of the following statement regarding to open circuit voltage and short circuit current of a PV panel will be correct when a change in the insulation occurs? Same I have already told you the short circuit current is approximately same as the IP. Photovoltaic current is directly proportional to the insulation. But open circuit voltage approximately NPTEL IP plus I naught divided by I naught. Reverse saturation current. Reverse saturation current of diode is very less. If you know about this one is I think in a nano ampere current 10 to the power minus 9, 1 into 10 to the power minus 9. This one is approx this that amount is a very low amount of current. So you can also neglect this term I naught by I naught because of IP is very high, approximately 8 ampere, 10 ampere defined for different solar cell. That's why you can also reduce, also neglect this term VOC approx of NVT into ln IP divided by I naught. This one is a very high. If you take a like, so this one is a IP is approximately take a 10 ampere. Of any panel is insulation current is 10 ampere. Then divide by 10 to power minus 9 half 1 9 ampere. It is very high. 10 to power 10 value. With respect to the 10 to power 10, 1 is very less. That's why you can neglect you can neglect I naught by I naught term in here. Okay. Then what are the questions? If insulation occurs changes, then what will be affected on the short circuit current and open circuit voltage? Changes VOC will be more than the change in ISC. This will be very wrong because of this one is a algorithm here. And IC is 90% of the insulation. It means short circuit current will be increased, more increase, and open circuit voltage will be lesser number of increase. Change in ISC will be more than the change in VOC. You can say this one. Both VOC and ISC changes at the same rate. No, one is linearly, second one is algorithm. Both VOC and ISC remains unchanged. No, it is depending on the insulation. You can also draw also IV characteristic. I already draw by different insulation. This one is VOCs, then ISCs. If increasing order of insulation. ISC is more increase, more changes, and VOC is less change. Okay. As temperature increases, the efficiency of PV cell. This one will be interested point. Temperature increases, then efficiency. Efficiency, what is efficiency of PV cell? The same as the maximum power. Efficiency is the same as the power. Maximum power divided by the input power. Output power is I will take as the VM, maximum voltage at the maximum power point, and the current at a maximum power point. Yeah, efficiency find input power is the insulation per unit area. Like if you can fix this 1000 watt per meter square is the standard at 25 degree centigrade. This is the standard insulation is 1000 watt per meter square at 25 degree centigrade. Then what is the voltage and current equation? You already know ISC is approximately IP. IP directly proportional to the insulation. Okay. It means if you increase that current temperature, then current will be increased. For any semiconductor devices, if you increase the temperature, the current will be increased. Means the effect of temperature on the power of PV panel efficiency. It means the current will be increased, but with respect to the voltage, what is the voltage? Voltage will be reduced. Some amount of voltage will be reduced if you increase the temperature. Think like a depletion layer. For simple purpose, think about the PN junction diode. This one is the depletion layer, like VD. If you increase the temperature, what will the VD depletion layer increase or decrease? Anyone? NPN junction diode, if we increase the temperature, then what will be the depletion layer? Will be increase or decrease? Of any semiconductor device, you know very well, if you increase the temperature, then the energy band gap is reduced. That is the, yeah, decrease. The voltage will be decreased because of the energy gap is be reduced. Then depletion layer is reduced. So depletion layer reduced, it means the voltage also reduced. And same phenomenon occurs in the solar cell also. If you increase the temperature, then voltage will be reduced. Then voltage reduced, current will be increased, but voltage will be more reduced with respect to the current increasing. That's why the overall power of solar PV will be reduced. It means insulation will be increased, but insulation, if you want to insulation increased, but temperature also want to increase. At that point, the voltage will be reduced and current will be increased, but voltage will be more reduced with respect to the current. That's why the overall power of solar cell will be reduced. That's why efficiency also reduced. VOC, you know about VOC, is approximately NVT to ln IP divided by of I naught. If you want to calculate the changes of VOC with respect to the temperature, then you find as VOC minus of VGO and VT divided by of temperature. Where Mn is the fixed for the semi silicon, VT is depending on the temperature, but the amount of to consider the whole thing, whole parameter of this one, then we will find the voltage will be reduced. Because of the here, Vt is directly proportional to the temperature, but I naught is directly proportional to T to power m e to power minus of Vgo n Vt. This m is like 1.5 for the silicon. This if this one is increased, it means that the whole algorithm will be reduced. IP by I naught will be reduced. Then log of, if you take a log of this thing, then we find the VOC will be reduced. That is in a mathematical expression you can find from here the VOC will be reduced, ISC will be increased. That's why the overall efficiency of a solar panel, if a temperature increases, then this will be decreased. If you observe this in practical cases, in summer time, efficiency will be reduced of a solar panel with respect to the winter time temperature because of the temperature. Next question, it will take like a module efficiency of a PV panel tested under standard condition of insulation like 1000 watt per meter square and temperature of 25 degree centigrade is given as the model efficiency is 20%. Efficiency is 20% at 1000 watt per meter square and 25 degree centigrade. The panel which has an area of 2 meter square, they are already given area is 2 meter square, is operational in a region where the present insolation will be reduced as a 400 watt. Insolation 2 can say like a 400 watt per meter square, and insolation 1 is 1000 watt per meter square. Next is given is assuming the panel temperature be the same as the standard temperature, the maximum power output in watt during this present condition. It means temperature will not change, only insulation will be changed. And in insulation will be changed, it means the efficiency will be same. Power will be reduced, but efficiency will be same. Efficiency depending on the only temperature. As temperature is given is the same, it means the efficiency will be, you can take as the same as 20%. Then you know about the efficiency of any solar panel of anything. P out will be into P in. P out will be taking as the maximum power. P in is the power at a standard version is given Pm divided by P in. P in is equal to insolation per meter square. It means the multiply of the area. In first condition, P in 1 is given as 1000 watt per meter square into area is 2 meter square. Then what is the P in 1? 2000 watt. Oh, okay. 2000 watt is the input power at 1000 watt per meter square insulation and 25 degree centigrade. Then calculate the maximum power at that point. It means the output power. Then Pm on is equal to efficiency into P in 1. Efficiency is 20%. You can say like a 22 into 2000 is equal to 400 watt. In the second condition, we ask about the maximum power Pm2 for efficiency will be same and P in 2. And second condition, what will be P in 2? Second input. Insulation into area. Insulation is given as insulation is 400 watt per meter square into area will be same 2 meter square is equal to 800 watt. Then what is the power? Efficiency is same as 0.2 into 800, 160 watt. Someone asked about the solve this problem based on the cell connected in series, but here is not mentioned says connected in series or parallel. You will taken only a cell panel, then use the whole model efficiency and model parameter only. It is not mentioned about the series and parallel connection. It will not also mention how much cell are connected in series or parallel. That's why you can't be solve like that in series or parallel connection in that question. The next question, as the intensity of light incident on a PV cell increases, then IV characteristic of the cell moves. Same as light up in light incidence in the intensity of light incidence means the insulation will increase. If you increase the insulation, then what will happen? Current will be increased more and the voltage will reduce. Voltage will increase less. Like that. ISC1, so I, V characteristic, ISC2, ISC3, ISC4, VOC1, VOC2, VOC3, VOC4, this one. Then you can observe this one, the whole of the characteristic is shifted to the upward because of the current will be increased more and voltage increase will less with compared to the current. That's why the whole of this one is the original. If you want to take this one original, then whole of the characteristic is shifted to the upward, not a downward, not left or right. This one you can say like a upward direction. We shifted to upward here. If you increase the intensity of light incidence, means the increase of the insulation. The data sheet of solar panel manufactured by a company named Loom Solar is given. Clear for the data sheet. The total number of monocrystalline per cell in a solar panel is described in the data sheet. This question related to the study of data sheet. I have already opened the data sheet of this one. This is the data sheet of that solar panel. Is given as the 144 cells monopers monocrystalline 1500 volt DC to 20.2% of maximum efficiency. I to ask in the question is only for the how many cells are connected. It will be 144 cells. If you want to check a data sheet here, this is given as the maximum power 440 watt and maximum voltage. Sorry, voltage at maximum power is at 42 volt and the maximum current at maximum power is at 10.5 ampere. Given open circuit voltage is given, short circuit current is also given, module efficiency is given 20.2%. This one is a standard irradiation like 1000 watt per meter square and cell temperature of 25 degrees centigrade is the room temperature. This one the reduced irradiance and 20 degree centigrade temperature. Then observe what will be changed. Maximum power will be change because of the radiation will be changed 800 watt. Voltage at maximum power also change, it will be 38 volt and previous is the 42 volt. Maximum current also change 8.55, previous is a 10.5, and open circuit voltage is 46.2 and short circuit current is 9.06. Here the previous one is the short circuit current will be 0.35. Here the efficiency is not mentioned. Then looks here, a temperature rating, effect of temperature on the panel. So like this one. At a short circuit current, I assume the short circuit current. Short circuit current have a positive coefficient of temperature 0.05% per degree centigrade. If you increase the temperature, then current will be short circuit current will be changed and increase at a 0.05% per degree centigrade. But same thing with respect to the current, the voltage is open circuit voltage looks here, the coefficient temperature coefficient will be negative minus of 0.28% per degree centigrade. It means the open circuit voltage will reduced, short circuit current will be increased when you increase the temperature. Then if you power is the multiplication of VOC ISC, then definitely will be reduced maximum power also. So given is the max power coefficient also negative 0.36% per degree centigrade. Here is the maximum system voltage given large number of final connected in series, that's why the 1500 volt. Operating temperature also given. Leave it, this one is the technical data, but this one is the mechanical data. Mechanical data is the number of cell here mentioned like 144. Cell type is given and cell dimension is given 166 into 83. 166 is length and 83 is the width. Then you can calculate the area of this one. From mechanical data you can calculate the area, and insulation is given 1000 watt per meter square and 800 watt per meter square. Then from there you can calculate the input power. Input power is the insulation into area. Area you calculate here, area you can calculate here, and insulation calculated there is sorry, not need of calculation is already given is the 1000 watt per meter square. But number of cells also connected like 144 number of cells, that's a total area. If you want to calculate the 144 into 166 into 83, this one is given a series and parallel connection of the cells 12 into 6 and 12 into 6. Okay, first question is given like ask about the how many cells are connected. This one is 144 is given. Then looks for the second questions. This one 144 data sheet panel. Again the total number of monocrystalline cells, total number of cells are connected is 144. Okay, from data sheet same thing is given the percentage module efficiency at standardization and the cell temperature. It means 1000 watt per meter square and 25 degrees centigrade. The two data is given at at a two insulation. First one is 1000 watt per meter square, second is 800 watt per meter square. But it's asked about the standard. Standard will be 1000 watt per meter square. This one. This one module efficiency is given. Module efficiency is 20.2 degrees centigrade. Sorry, 20.2%. Next question is given like the cell dimension are given in the mechanical data in data sheet. Then calculate the panel efficiency. Panel efficiency, you know about P in into P output divided by P in. P output same as maximum power divided by input power. This one is a Vm into Im. P in the insulation into area. Insulation we can take a standard at a standard is 1000 watt per meter square. Then what is the area? Area is given as 166 into 83 mm. It means 166 mm into 83 mm. You can for one cell. The number of cell is 144. Then you can calculate a panel efficiency. Ask about the panel efficiency is the whole number of cell. Then 144 into 166 into 83 is the mm. Okay, is given in mm, but your power is per meter square. Then change is the mm into meter. Then 10 to the power minus 3, 10 to the power minus 3. If we calculate, then the whole is 10 to the power 6 minus 6 meter square. Then calculate this one, 144 into 166 into 83. Divide by 10 to the power 6 is 1.984 meter square. Then what will be the input power? Insulation into area, 1000 watt per meter square into 1.984 meter square. To calculate in kilowatt, then divide by the 1000. This one 1000 will cancel out, the same as 1.984 kilowatt the input power. Then what will be the output power? Output is the Vm into Im. Take a data from a data sheet, maximum power and maximum current at a standard. Maximum power voltage as maximum power is 42 volt, and current at maximum power is IMP is 10.5. Take this one. Sorry. Is equal to 441 watt. Then what will be efficiency is P output over by P in 441 divided by 1.984. Sorry, this one is the watt. Then what will be kilowatt? 0.441 kilowatt. Both are in the kilowatt. Then take the kilowatt. Take data in at the same parameter. It will be 0.22227 is, if you ask about in percentage, 22.22%. Okay. Next, data sheet is already given here. What is the minimum fill factor of solar PV module at temperature of 25 degrees centigrade? From the given data sheet, module efficiency is given here. The maximum power is given. Open circuit and short circuit open circuit voltage and short circuit current is given. At the same standard insulation, irradiation. Fill factor, you know, maximum power divided by of maximum VOC into ISC. The maximum power is given 275 watt plus minus of 3%. Then lowest given is the minimum power fill factor. Minimum fill factor occurs at the minimum output power. It means the reduce of 3%. Then 275 reduce of 3%. It means 97%. Divided by VOC and ISC, 38.6 into 9.48. This one will be 266.75 by 38.6 into 9.48. 365.928. Fill factor is 0.7289, will be equal to 0.73. Given a minimum fill factor. Sorry. Minimum fill factor occurs at the minimum output power. Sorry. Calculate the open circuit voltage and short circuit current from the for the data given in equation 6 at temperature of 45 degrees centigrade. Previous data is given at 25 degrees centigrade, T1. Next is given is the when what happened when sorry, when we will increase the temperature at 20% to the 25% to the 45%. And also all of the data, open circuit voltage and short circuit current at a 45 degrees centigrade. This one is T1, this one is T1, T2. In data sheet is given as VOC 38.6 volt. Temperature coefficient is given here. Voltage temperature coefficient is 1.37 into 10 to power minus 1 volt per centigrade. And current coefficient is given 5.56 into 10 to power minus 3 ampere per degree centigrade. You can observe here also, from here you can also observe this one. Short circuit current is the temperature coefficient of short circuit current is very less which compared to the changes in very less as compared to the open circuit voltage. This can be written as 0.00556 ampere per degree centigrade in positive, but this one is negative point is written as 0.137 volt per degree centigrade. Even this one will be more change with respect to the short circuit current. That's why the power will be reduced. Okay, I written as VOC1 is equal to 38.6 volt. ISC1 is equal to 9.48 ampere at 25 degree centigrade. Second is then VOC2 is equal to VOC at 45 degree centigrade is equal to VOC at 25 degree centigrade plus delta V changes. So what will be delta V changes given as a minus of 1.37 into 10 to the power minus 1 per degree centigrade. So how much degree centigrade will be changed? Like final temperature minus initial temperature. Minus 1.37 into 10 to the power minus 1 into 20. Sorry. Minus of 2.74 volt. Then what will VOC? Second opens. VOC at 25 degree centigrade at 38.6 volt minus of 2.74 volt is equal to 35.86 volt. Same is applied for the short circuit current. 2 is equal to short circuit current at 45 degree centigrade is equal to short circuit current at 25 degree centigrade plus of delta I. So what will be delta I? Same thing, temperature coefficient of current 0.00556 ampere per degree centigrade. Then 0.00556 degree per centigrade into temperature changes 0.11 ampere will increase. And then ISC2 is equal to say 25 degree centigrade 9.48 plus 0.11 9.59 ampere. This one will be at 45 degree centigrade 35.86, 35.86 and 9.59. Okay. Question given, what is the insulation level in watt per meter square for a module efficiency of 50% and the maximum output power of 198 watt? Area is given of the module is this one in square mm. Efficiency is given 50%. Okay. Maximum power is given, PM is 198 watt. Insulation level is okay. You know about the final efficiency. Module efficiency is maximum power divided by a input power, same output power, input power. Output power is the maximum power and our input power is the insulation power. Then insulation into area. First one, find the area. Area is given 1662 into 990 mm square. Calculate into meter square, then divide by 10 to power 6. Then we find 1.662 into 0.990 meter square. 1.662 1.64538 meter square. Area is fine. Efficiency is 50%. You can written as 0.15. Maximum power is given 198. Then what will be the insulation? Insulation is the maximum power divided by area into efficiency. 198, area is 1.64538 to efficiency 0.15. It 02.24 watt per meter square. Same as 795 to 805 is given the range of 10. This one is in this was the last question. A photovoltaic cell of a solar PV model has following data. Diode reverse saturation current is 1 nanoampere. Diode reverse saturation current I naught given as 1 nanoampere, written as 1 into 10 to 2 power minus 9 ampere. Okay. Next one, volt equivalent of temperature is means Vt. T divided by 11,600 volt. At a room temperature, you know about T in Kelvin, and at room temperature of 300 Kelvin divided by 11, that it will be approximate of 25 millivolt, 26 millivolt. I think you know, you all know about this one. Vt is equal to 25 6 millivolt approx. Sorry. Anyway, photo current is IP 8.6 ampere. Diode ideality factor is N. E to power diode current is like I naught into e to power V divided by NVT, whereas in N is equal to ideality factor of diode, 1.4. If there are 16 number of cells are connected in series, series connected cells, it means voltage will be added in series in one module. Then what is the open circuit voltage of module in volt? You know already I is equal to IP minus of I naught e to power V into I V plus I into RS divided by NVT minus 1 minus of V plus I into RS divided by of RS. This will be current equation of a PV cell. Then what is the open circuit voltage? You know, circuit is open, current will be 0, I will be 0, V is equal to VOC, same as BBS. 0 is equal to IP minus of I naught e to power VOC divided by of NVT minus of 1 minus VOC RSS. Already given is the RSS very high with respect to the series resistance. Photo current is much higher than the current through the shunt resistance. For finding the open circuit voltage, you can neglect this one term because of open circuit voltage is very less of a cell, not a module. If you number of module connected, number of cell connected in a series to form a module, then module voltage will be increased. But in cell voltage, open circuit voltage of cells are cell is very less. I calculate with this one. Wait, is equal to IP minus of I naught. Then you can also observe this one. What will be the open circuit voltage? NVT minus of 1. Then what will be the VOC? VOC is same as NVT into Ln IP divided by I naught IB plus I naught divided by I naught. I naught is given as 1 nano ampere. It means of 10 to the power minus of 9 ampere. IP is given 8.6 ampere. Then what will be IP divided by of IA? Not. It will be very high. That's why I say that I naught by I naught will be neglected. Into 1 into 10 to the power minus 9, and you can say that 8.6 into 10 to the power 9. If you take a whole on, this one will be 8.6 into 10 to the power 9 plus 1. With respect to this one, only one will be very relative, very less. That's why you can neglect one term from here. N is given 1.4, Vt is given 26 millivolt, 26 into 10 to the power minus 3 volt. And what will be the VOC? 1.4 into 26 into 10 to the power minus 3 ln of 8.6 into 10 to the power 9. If you calculate this one, VOC of a cell, a single cell, will be 0.8326 volt. This one is a cell open circuit voltage. Will be come at less than 1 also, less than 1 volt. That's why I will neglect this one, VOC divided by RSS. RSS is very high respect to this one. Then what will the total open circuit voltage of module? Open circuit voltage of module. 16 number of cells are connected in series. into a, a cell open circuit voltage 0.8326. If you can multiply this one, we will find 29.956 approx of 50 volt. Answer is given like 46 to 54. Middle of this one is 50 volt. Other question number, last question 14. At a standard temperature like 25 degrees centigrade, okay everyone, sorry. From this session you can observe this one, or if you want to change the insulation, if insulation will change, then current will be more change respect to the voltage, open circuit voltage of a cell. And if you temperature is increased, then current will increase, but voltage will be reduced. With respect to the current, voltage will be more reduced when you increase the temperature. That's why the overall power also reduced. Then efficiency also reduced when you increase the temperature. Two important thing comes from there. And you also did the parameter or data sheet of solar panel. Will you find assignment number 2 also? And second assignment question I will explain in next session. I can't be explain in that session because of the your assignment session is not over. That's why it will be restricted. You can't be run as same assignment which one given by you by NPTEL to you. I can I can teach you related to that, but can't we exact this one question, that question related to that one. I can explain, but I can't explain the same question. Then okay everyone, I want to exit this one.